Have you ever looked at a really compelling research study and just found yourself wondering, are these results really as solid as they look?
hmm
Or if, just maybe, the way they collected the data might have kind of nudged the findings?
Yeah, that little voice in the back of your head, it happens.
Exactly. It's a thought that crosses a lot of minds, I think, and today we're actually taking a really close look at that exact kind of challenge. We're doing a deep dive into something critical, but honestly, often kind of overlooked in quantitative research.
Yeah.
It's called common method bias.
Right, CMB.
Yeah, and it's not just some small statistical quirk. It's subtle, almost like an invisible contaminant that can seriously skew study outcomes. And the researchers, they
Mhm.
might not even realize it's happening.
Which is the scary part, really, leading to conclusions. That might be.
Well, misleading is putting it mildly sometimes. Definitely. So our goal today is to really unpack what common method bias is, look at how it quietly messes with research findings, and most importantly, introduce a powerful, pretty practical way to spot it. We're going to focus specifically on how it affects things within a framework lots of researchers use called partial least squares structural equation modeling, or PLS-SEM.
hmm And we're drawing heavily from a really key article here, a 2015 paper by Ned Kock. It's titled Common Method Bias in PLS-SEM, a full collinearity assessment approach. And what's great about it is that it uses these Monte Carlo simulations, really clever way to clearly show both the problem and a potential solution.
Okay, perfect. So to take us off, let's just set the scene a bit. I know many listening will know SMN, structural equation modeling, inside and out, but maybe just a quick refresher. Like, how does SM work with things like latent variables and questionnaire data, setting the stage for where this bias thing can creep in?
Absolutely. So SEM, at its heart, it builds on something called path analysis. Goes way back to Wright, actually like the 1930s, 1960s. Originally used in evolutionary biology, believe it or not, to look at causal assumptions.
Mm,
But today, yeah, researchers use it to build these sophisticated models, trying to map out how different variables might influence each other.
okay.
And the key thing here, like you mentioned, is latent variables. These are concepts you can't measure directly. Think of collaborative culture in a company, or maybe competitive advantage.
Right, you can't just put a ruler on culture.
Exactly. They're kind of like icebergs, right? You can only directly measure the tips, those visible indicators.
Sure.
Often questions on a questionnaire, usually using numeric scales like a 1 to 7 Likert scale maybe. But what you're really trying to understand is that big hidden concept underneath.
Gotcha.
And just quickly, there are two main flavors of SEM, covariance-based, which is one type, and then PLS-based SEM, or PLS, SEM. And that second one, PLS-M, is really widely used in fields like e-collaboration, which is where the examples in Koch's paper come from.
Okay, so we're building these models, often with survey data, trying to get at these deeper latent concepts, which leads us right to the main event. What exactly is common method bias? And maybe more importantly, what makes it so sneaky? How does it actually affect the results we see in a study?
Right. So common method bias, the crucial thing is it's not caused by the real network of causes and effects you're trying to model. It comes from the measurement method itself.
How so?
Well, think about a questionnaire. Maybe the instructions at the top subtly steer people towards answering in a certain way across the board. Or maybe there's just an implicit social pressure, social desirability that makes people kind of shade their answers similarly on different items. That shared influence, that common variation, that's not about the actual constructs. That's common method bias.
Okay, so it's like an external factor bleeding into the answers.
Exactly. Mathematically, you can think of it as adding this little extra bit, this common method variation, to all the indicators you're measuring.
Ah.
And because the latent variables are basically summaries or aggregates of those indicators, this shared variation, this sort of noise, it artificially inflates the level of collinearity among those latent variables. They start to look more related than they truly are.
And the knock-on effect.
The predictable outcome is that your path coefficients, the numbers that show the strength of the relationships in your model, get artificially inflated.
So they look bigger, stronger than they should.
Precisely. It's like this bias secretly turns up the volume dial on your findings.
Okay, that makes sense. And the paper illustrates this.
Yeah, the Koch paper uses a really clear illustrative model. It's inspired by actual e-collaboration research. It has 3 latent variables, one for collaborative culture, one for e-collaboration tech use, and one for competitive advantage. And each of those was measured with 6 indicators, thinking about the firm as the unit of analysis.
Okay.
And to really show the bias effect, they did this Monte Carlo simulation.
Yeah.
Basically, they created two big data sets, like 300 simulated survey responses each, using those 1 to 7 scales.
One clean, one biased.
Exactly. One data set was intentionally contaminated with common method bias. They built that shared noise right in. The other one was clean. And the brilliant part was they knew what the true relationships, the true path coefficients, were supposed to be in the underlying model. They set them at 0.45, for instance. And they also set the common method effect size in the biased data.
Ah, so they had a perfect baseline for comparison.
Precisely. Allows you to see exactly what the bias does.
So running the analysis on both data sets, what was the actual result? What did they find when they compared the clean versus the contaminated model? What was the real world consequence?
Well, the headline finding was definitely this path coefficient inflation. It was really clear. In the model with a common method bias, every single path coefficient was noticeably larger than in the clean, unbiased model.
How much larger are we talking? Like just a tiny bit or?
No, quite significant. For instance, a path coefficient that was truly 0.447 in the clean data jumped up to 0.625 in the biased data. Another one went from around 0.357 up to 0.435.
Why?
Yeah, these differences weren't trivial. They ranged from over 20% to nearly 40% inflation on those paths.
Yeah.
That first example, the jump from 0.447 to 0.625, that's almost a 40% increase.
That's huge. And the danger there is?
The big danger is making what we call type I errors, false positives. You conclude there's a significant causal link maybe between, say, tech use and competitive advantage, when really a chunk of that apparent relationship is just this measurement artifact, this bias.
So you might publish findings saying X causes Y based on results that are artificially pumped up.
Exactly. It can also, theoretically, lead to type 2 errors, false negatives, masking real effects, but the paper really focuses on this inflation problem.
Okay, that's a really powerful demonstration of the impact, which immediately makes you think, surely your standard checks catch this, right? Like confirmatory factor analysis, CFA, we use that all the time to check our measure.
Ah, yes, the CFA question.
What did the paper find there? Can CFA sniff out this bias? Because honestly, if it can't, that's concerning.
This is probably one of the most crucial takeaways, I think. Because intuitively, you'd absolutely expect a robust technique like CFA to flag this kind of problem. But the research, including Kock's simulation, shows pretty clearly that CFA is largely ineffective at identifying common method bias.
Really? Wow, okay.
Well, let's break it down. First, think about convergent validity. That's where you check if your indicators load strongly onto the latent variable they're supposed to measure. Usually you want loadings above, say, 0.5 or 0.7.
Right, standard check.
In Kock's simulation, both models, the clean one and the biased one, pass this test easily. But here's the kicker. The common method bias actually artificially increased the loadings.
Wait, it made them look better?
Yes. An indicator that truly loaded at, say, 0.742 in the clean model appeared to load at 0.902 in the biased model. The bias made the measures look more convergent, stronger than they really were. It creates this false sense of security.
Okay, that's counterintuitive. What about discriminant validity, making sure constructs are distinct?
Same problem, unfortunately. Discriminant validity is often checked by comparing the square root of the average variance extracted, the AVE, for a construct with its correlations with other constructs. The idea is a variable should share more variance with its own indicators than with other variables.
Okay.
Now, common method bias does increase the correlations between the latent variables, which you might think would flag a problem. But it also increases the AVEs at the same time because, remember, it boosts all the indicator loadings.
Ah, so both sides of the comparison go up together.
Exactly. They rise in tandem, effectively canceling each other out in the context of the test. So, again, both the clean and the biased models showed acceptable discriminant validity according to the standard criteria. The test was undermined.
So neither convergent nor discriminant validity tests, as typically run in CFA, are reliable for catching this specific bias.
That's the conclusion from this research, yes. They just aren't sensitive to it. In fact, the bias almost exploits the logic of those tests to make things look better than they are.
That is genuinely sneaky. Okay, so if CFA, which is a cornerstone for so many of us, isn't the answer here, what is? What does the Kock paper propose as a solution?
Right, so if the traditional toolkit isn't quite up to the job for this specific problem, we need something else. And the paper champions the full collinearity test, building on work Kock and Len published earlier.
Full collinearity test. Okay, what does that involve?
It's designed to be a more comprehensive assessment. It looks for collinearity, essentially too much overlap or redundancy among the latent variables in your model, considering all variables simultaneously. It specifically assesses two things: vertical collinearity, which is when predictor variables might be measuring basically the same underlying thing, and lateral collinearity, which is when a predictor variable might be too similar to the outcome variable it's supposed to be predicting.
So it's looking for overlap from different angles.
Precisely. And the key output metric it generates is called a variance inflation factor, or VIF, for each latent variable in the model.
VIFs, okay, I've seen those used in regression.
Similar concept, yeah, but applied here within the SEM context to the latent variables. And Kock proposes a specific threshold. A VIF greater than 3.3 should be considered an indicator of pathological collinearity. And crucially, in this context, it serves as a warning sign that your model might be contaminated by common method bias. If all your VIFs are at or below 3.3, the model is likely clear of this specific issue.
And did it work in your simulation? Did it catch the bias that CFA missed?
It did. That's the compelling part. In the clean non-CMB model, all the VIFs were comfortably below 3.3, like 1.5, 1.4, 1.7. Totally fine.
Okay.
But in the model, with common method bias, while a couple of the VIFs were still under the threshold, one of the latent variables produced a VIF of 3.720.
Ah, above the 3.3 cutoff.
Exactly. It correctly flagged the model as problematic, identifying the presence of the common method bias that the other tests missed.
And why does it work where CFA doesn't?
It makes logical sense, really, because as we discussed, common method bias works by artificially increasing the overall level of collinearity among the latent variables. The full collinearity test, by directly measuring these VIFs, is tapping right into that core symptom of the bias.
Got it. So it's directly measuring the thing the bias causes.
Exactly. Now, it's fair to say there is some debate out there in the methods world about common method bias.
Yeah.
You have researchers like Spector back in '87 who kind of controversially called it an urban legend.
Right. Always good to acknowledge other perspectives.
Absolutely.
Mm-hmm.
But then you have others like Podsakoff and colleagues in 2003 who take it very seriously and offer really practical strategies for preventing it in the first place during data collection. And prevention is always the best cure, right?
Ideally, yes. Stop it before it starts.
But if prevention wasn't possible or wasn't enough, and this full collinearity test does flag potential CMB in your data, what then?
Yeah, what are the remedies?
The source paper, Kock and Lin, 2012, outlines several steps you can take to deal with the collinearity once it's identified. Things like carefully removing specific indicators that might be causing problems, maybe reassigning an indicator to a different latent variable if it fits better. In more severe cases, you might even consider removing an entire latent variable, or maybe aggregating two related latent variables into a single, broader construct. There are statistical approaches too, like hierarchical analysis.
Okay, so there are options, but they involve modifying the model.
Yes, careful adjustments based on the diagnosis from the VIFs.
Okay. Are there any other sort of broader points or nuances we should keep in mind about this?
Yeah, a couple of important things. First, model complexity matters. These full collinearity VIFs tend to naturally increase as your model gets more complex, more latent variables, more paths.
Why is that?
Well, just more opportunity for overlap, right? More chance that the perceived meaning of different questions or facets of constructs starts to blur together for respondents. So the relatively simple three-variable model used in the Kock paper was actually a pretty conservative test. In bigger real-world models, the VIFs triggered by CMB might be even higher, even more obvious.
That makes sense. More moving parts, more potential for issues.
Right. Second point is about the specific PLS-SEM algorithms people might use. The classic algorithms are actually quite good at reducing model-wide collinearity, but sometimes they can overcorrect, they can attenuate the path coefficients, push them down a bit too much.
Okay.
More recently, researchers have developed what are called factor-based PLS-SEM algorithms. These handle measurement error differently and tend to produce slightly higher, but arguably more accurate, VIF values.
So the 3.3 threshold might not apply universally.
Exactly. It might need adjustment. Kock and Lin actually suggest using a higher threshold, maybe a VIF of 5, if you're using algorithms that explicitly account for measurement error, like these newer factor-based PLS methods, or even traditional covariance-based SEM. So know your algorithm, know your threshold.
Good practical advice.
And finally, while we've used examples from e-collaboration and mentioned specific software like WarPLS, the core principles here, the problem of CMB, the limitations of CFA for detecting it, and the utility of the full collinearity VIF test they apply broadly.
So this isn't just an e-collaboration issue.
Not at all. Any field using path analysis, using SEM with latent variables measured by indicators, psychology, marketing, management, education, health sciences, you name it, this is relevant.
Okay, that's a fantastic overview. So wrapping this up, what's the key takeaway for everyone listening, whether they're students, researchers, or just, curious people trying to understand studies they read?
I think the main message is common method bias is real, it's sneaky, and your standard checks might not catch it. But crucially, there are tools, like the full collinearity test using VIFs, that offer a practical and effective way to identify it. This deep dive should hopefully equip you to ask tougher questions about how data was gathered and analyzed, and maybe look at reporting findings with a slightly more critical eye, especially when everything looks maybe too perfect.
Absolutely. Be aware of the potential pitfalls.
Yeah. And maybe a final thought to leave everyone with, something to chew on. If the very way we collect data can silently inflate results or even hide true relationships like we've seen here, what other hidden biases might be subtly shaping the information we encounter every single day? And how vigilant do we really need to be in asking not just what the finding is, but digging into the how behind it?